Hello. Hi everyone, I'm David Feng and I'm here with Nick Barnes and Chris and Xiaodi Yu from the Australian National University and Data 61 and Chris McCarthy from Swinburne University. And today I'll be presenting a new way of performing salient object detection. Salient object detection is a task of finding interesting objects in an image. Incorporating depth information can be helpful when the foreground and background have similar appearance. However, challenging cases arise in depth when the foreground has relatively low depth contrast compared to the background. Existing methods are based on depth contrast features, which assign saliency according to the depth difference between an object and its surroundings. So if we have a foreground patch P1 at a certain depth, and a background patch P2 with greater depth difference to its surroundings, then contrast methods will assign P2 a higher saliency than P1. And this can be seen in the output saliency maps of existing methods. We propose a new way of measuring saliency called local background enclosure, which aims to measure the degree to which a candidate patch is enclosed by its local background set. So the local background set is defined as a set of patches within a radius having greater depth than the candidate patch. In this example, P1 has a higher saliency than P2 because it's in front of its surroundings for a larger number of directions and thus is more enclosed by its local background set. And this is what the enclosure saliency map looks like, where we correctly identify the foreground structure in this image. In order to measure enclosure, we use two angular statistics. The first is angular fill, which records the proportion of the angular region around the candidate patch that intersects with the background set. The second is angular gap, which is based on the size of the largest angular region that does not intersect with the background set. And this could be thought of as a foreground-only region. So if we look at the background patch P2, you can see it has a similar angular fill value to P1, but a lower angular gap score, and thus is less salient. So the final enclosure value is computed by integrating these two functions over a range of background sets and taking their product. Here are the results on the two major RGB-D datasets. Our method gives at least a 10% improvement in performance compared to depth contrast features on both datasets. Now I'll go through a few examples to illustrate why our method gives improved results. Firstly, we reduce false positives and negatives when the object has a relatively low depth contrast compared to the background, such as a truck in this image. Contrast-based methods will mark the dumpster as salient because it has the highest contrast, whereas our method correctly identifies the truck as salient based on its foreground structure. We also reduce false negatives when the object has a relatively large range of depth values in the image, such as a mask. Depth contrast methods will produce a varying saliency response across these types of objects. However, since different points on the same object are more likely to have similar enclosure values, our method produces a more uniform saliency response. When we embed our feature into a standard saliency approach with priors and graph cut refinement, we achieve state-of-the-art results, which are shown here. So from left to right, we have RGB, depth, ground truth, our method, and then three competing methods. And false positives are shown in red. As you can see, using enclosure to measure saliency produces a better indication of foreground structure. And that's it. Thanks for listening, and see you at poster stand number 9.